Welcome. So in this video, we're going to look at an application of arc length. So let's read the problem. An ellipse in the xy plane can be described using this vector value function here. So that's a cosine t comma b sine t. Kepler's first law tells us that each planet has an elliptical orbit about the sun. The Earth's semi-major and semi-minor axes are 1 AU and 0.999. AU, respectively. AU stands for astronomical unit. So let's go ahead and use arc length to calculate the length of the Earth's orbit in astronomical units. So before we go further, recall that given a vector valued function of this form, and I don't know why I used a derivative there, excuse me. So we have an x component named f and a y component named g. The arc length s, and that looks too much like an integral symbol, so let me redo that. S equals the integral, now from some start to some end, of the square root of the derivative of f of t squared plus the derivative of g of t squared with respect to t. So in our case, f of t is equal to a cosine t, and g of t is equal to b cosine of t. Excuse me, sine t. Sorry for all these typos. It is like 10:38 my time, and it's been a long day. So, they're kind of calming as my brain is not as caffeinated as it was, like, say, 12 hours ago. Okay, so let's use this to compute the length of the Earth's orbit. Oh, before I do, f prime of t in our case would be negative a sine t, while g prime of t is b cosine of t. So our arc length, let me quickly draw a picture and you'll see why I'm drawing this. If you bear with me. I don't know why my app flipped this ellipse here, but maybe you get an idea of what I'm doing. Now, there we are. So let's say this is our elliptical orbit in the xy plane. Right? And it doesn't matter which side or which end I label A and which end I label B on which axis, doesn't matter. So I'm not going to label A's or B's here. What matters is that we get an intuition for the fact, or recall, that starting here and going all the way around, well, that is an angle of 2 pi. That is a rotation to go all the way around. It's 2 pi. All right then, so let's go ahead and start our integral at 0. And then it's tempting to put 2 pi here. And I guess I should do it at least for the first step. Okay, I'll do it for the first step, just because I do not want to lose anyone along the way here. So I'm going to write a sine squared t plus b squared cosine squared t. And I just caught another typo here. Why did I write b equals cosine of t here? That makes no sense. Sorry. I would drink some caffeine to make this video better, but then I can't get to bed after I'm done making this video. So I'm chugging along my uncaffeinated self. There we go. Now let's go back to what I wanted to do and just held off on a little bit. Well, instead of, say going all the way to 2 pi, notice that, well, if we go halfway around, that's pi. This half and this half are equal. So we could just double this and go to pi. But it gets easier, actually. Because look here. This quarter and this quarter and this quarter and this quarter are all equal. So we really can just go to pi over 2 since these are all equal here. So let's rewrite this. I'm going to rewrite this arc length as the integral from 0 to pi over 2. And those of you going, that's another typo. She's really tired. No, this is intentional. If you see it, just hang tight. A squared sine squared t plus b squared cosine squared t dt. Well, I can't just change the limits of integration and expect these to be equal, since I'm just integrating this part here, figuring out this arc length. That's only 1 out of 4, so this is 1, 2, 3, 4. I need to quadruple this integral here. There we are. See, it wasn't a typo. That one was on purpose. Now, this is something that we can't really integrate using techniques that we have at hand. So I'm going to go ahead and pull up GeoGebra, and I'm going to try to split screen it because I really don't want to have to edit a video after this. I want to go to bed. So let's see, where's GeoGebra? Here it is. There it is. Hey, and that's kind of, hey, there we go. That worked out okay. So there we are. Okay, so I'm going to go ahead and type in int, so integral. I stopped spelling it because I was worried that I was too tired to actually spell it correctly. And this is the square root. Oh, and actually, before I go any further, I'm going to just change this one more time. And there I go, making my s's look like squat integral symbols. This is the integral 4 times the integral from these limits, 0 to pi over 2. I'm just going to arbitrarily pick. I'm going to say let a equal 1 and b equal 0.999. Well, 1 squared is just 1, so this is now sine squared t plus 0.999 squared cosine squared t. Let's make sure to sketch our square root all the way out. And I also really like having zeros before the decimal place, because otherwise I make these dots so small that sometimes they look like whole numbers to me if I don't put a 0 there. So now I know what to type. I'm going to go here to function and type sine. And I'm not going to use t's. I'm just going to have x, this little arrow here, to get the square plus then 0.999 squared. Function again, cosine x squared. And I want to integrate with respect to x from 0 to pi over 2. And of course, I forgot to quadruple it. And you guys didn't see this because I edited it out. So this is the second time I put it into GeoGebra, forgetting to quadruple it. And I bet there's going to be something else wrong. 4 times. And I think I know what it is this time. It is this x here that is screwing it up. So let me remove this x. There it is. All right. So the arc length is 6.28. So what does that tell us? The Earth's orbit about the sun is 6.28 astronomical units. Okay, keep calm and math on, preferably when you're caffeinated. Good night.